are doing here. Few words about myself. As you see, I am Professor Emeritus of Chemistry, and my career, or at the beginning of my career, I was studying spectroscopy. I have done various kinds of spectroscopy: Stern-Gerlach spectroscopy, absorption spectroscopy in the vacuum, ultraviolet, magnetic circular dichroism in the vacuum, ultraviolet. But then in 1994, I think, one of my grant applications was rejected. And I realized that in 2 years, I will be dead scientifically. So I made a decision to leave spectroscopy and to move to another field. At that time, nanotechnology was already a word that attracted people. So I said, okay, I am moving to nanotechnology. But how can you move to a new field? Nobody heard about you. Who is going to give you a penny to do research about this field? But it so happened that at that time, I read a book on sonochemistry. And in the introduction, the author said that the equipment to do sonochemistry is rather very cheap. I said, okay, something new, cheap equipment. I have some reserve. Let me spend my reserve on buying the equipment. Okay, I bought the equipment. But still the question is, how is it related to nanotechnology? By chance, I read at that time a paper in Nature in which somebody has done the sonochemistry of iron pentacarbonyl, FeCO5. And the results were he got a powder made of iron, but the iron had two excellent qualities. First of all, it was 10 to 20 nanometer size particles. Secondly, it was amorphous. The iron was not crystalline, it was amorphous, which by itself has some properties that I will not delve on it today. So I said, I'll jump to the water. I'll start at this direction, making nanoparticles of metals. And since 1994 to 2004, I have indeed worked mainly in developing techniques by which I was able to prepare nanomaterials. You see, on the left-hand side, the upper left, you see basically sonication, sonochemistry, that you put a sonicator in a test tube that is cooled, and and you do a reaction. On the left, you have a microwave oven that you cook food in. But the microwave oven was modified, and I have passed through it a distillation column. So that's microwave, second technique. Down here, you have what we call sonoelectrochemistry. Number 3 on the list. What is sonoelectrochemistry? It is basically electrolysis, but the electrolysis is done in a very smart way. You pass a DC current, but a short pulse of DC. So the cations are being reduced and assembled on the cathode. But the electric pulse, the electric short pulse, is followed by a sonopulse. But in this case, the sonopulse doesn't do chemistry. What it does is shaking the electrode, and down to the test tube, you get nanoparticles. And this way we were able, for example, to prepare magnesium nanoparticles, aluminum nanoparticles. There is no reduction, not a lithium aluminum hydride or any chemical that can reduce magnesium or aluminum. You might say sodium can reduce, but you don't want exactly to work with sodium. It's not the very convenient chemical to work with. And on the bottom right side, you have what we call a swedge lock. This is used to connect pipes, and we have used it as a high pressure cell. And we have developed many reactions in this cell at high temperature, and we call this technique RAPET. RAPET stands for reactions under autogenic pressure at elevated temperature. So these are the 4 techniques by which I have prepared many materials. But in 2004, I said to myself, okay, you have published 70, 80, 90 papers describing how you prepare various materials, nanomaterials. What's next? So in 2004, I have decided to move to practical, to applications of nanomaterials. And over the years, in addition to publishing another 700 papers, I have worked on antibacterial textiles, antiviral textiles, on conversion of biomass to biofuels, on many applications related to nanomaterials. And in fact, on the market, there are today, well, I would say 2 products that came out from my laboratory and are being sold, and the university gets royalties. One is a mask, a face mask that is antiviral against COVID-19, and the other one is a cream that for older or semi-older people is supposed to make your skin, the face skin, a little looking better. So you see, applications came out. So energy sources, you know all this, I don't have to, solar, biomass, the origins. Now I want to start with preparation of biodiesel. We have prepared the biodiesel from vegetable oils. You see here on the left-hand side, triglyceride. We went to the supermarket, bought canola oil or corn oil, any oil was okay. You reacted with methanol, you get back with a catalyst, of course. The regular catalyst, as you can see at the bottom of this slide, is NaOH, KOH, or sulfuric acid. And you get as a product glycerin and the methyl ester of the fatty acid, which is called FAME. And this is basically the biodiesel. Now, what was known before me was that this reaction can be carried out in a microwave oven in very short time. On the other hand, it was known that solid catalyst, like strontium oxide, is also a very, very good catalyst for this reaction, which is called transesterification. So I have decided to join them, namely to do the reaction at a microwave oven and to use strontium oxide as a catalyst. At the end of the reaction, you see on the right-hand side, biodiesel as an upper layer. Down you have the heavy layer of glycerol, and the catalyst is in between. You can collect the catalyst and reuse it in another reaction. Now, the most important thing is that this reaction goes to completion, 100% disappearance of the oil, 100%. You see, and you get 99% for conversion according to the upper in 40 seconds. That's very good. Now, what happened is that we have sent the paper for publication. But then we faced a very stubborn referee. And he said, oh no, I don't accept this paper because although it's 40 seconds, very nice, maybe a world record, but there was no stirring. I want these people to stir the reaction. And indeed, after a few conversation or disputes with this referee, we have said, okay, let's take the bottom part and introduce the magnetic stir the reaction. And indeed, it shortens the reaction. And today, you can finish it in 10 seconds, and as you see in red, and 100% conversion. We have based the analysis on NMR, and by the way, using KOH, you can read, under the same condition leads to 83% conversion, and we are getting 100. But then you might say, well, today, I don't know in Turkey, but in Israel, to buy a liter of supermarket oil is about 12 shekels. That's our currency. So even if I convert fully, and it's not full because you have glycerol, you have to remove the glycerol. And so out of a liter, let's say you get a half a liter. So half a liter of biodiesel for 12 shekels, while at the pump, you are paying less than 5 shekels for a liter of gasoline. What is the idea? That's very expensive. So we went on, and we went to cooked oil. We went to a restaurant and collected the cooked oils that are wastes, basically. We filtered it from big particles, and the same happened, namely, in 10 seconds, full conversion, but this is a cheaper price of the starting material, and we were happy. And here, in this slide, you see that we have taken out the strontium oxide and repeated the reaction 4 times, and we are getting nice percentage of conversion. Maybe we are losing a little bit, but it's still above 196, and we were still happy. It can be reused, the strontium oxide, the catalyst. Now, still there is a problem, because supermarket oils comes from cultivation of grounds that if you are using the product, let's say the oil, the olive oil or canola oil, if you are using it for production of oil, of biodiesel, you are competing with a food price. So people in Guatemala, I think, started to complain. Their food price of these products went up, and it became clear that this is not the smartest way. So we have decided to get biodiesel directly from microalgae biomass. To grow microalgae, as you will see in a moment, you don't need cultural or agricultural grounds. You don't compete with the food price, and it's what we have done. we found a company that doesn't exist anymore. It went bankruptcy, that was growing a microalgae called Nanotechnology. They grew it next to the power station, taking the carbon dioxide that came out of the chimneys, and it was also close to the beach, so the water was seawater. So you might say the two starting materials, carbon dioxide, comes also almost for free, and seawater for sure for free. So it was a cheap way to grow it, and it was grown to 7 days. And what they provided us, here are the pools in which the microalgae is grown. And on the right-hand side, you see the powder that we were using. At the beginning, we thought that to go a long way, namely to take the powder and to separate the lipids. And then the triglyceride will be converted to biodiesel. But then we became courageous and we said, let's work directly on the dry biomass and it will save money, it will be faster, and let's see if we get biodiesel. You see, here at the upper line, you see Nanotechnology biomass converted by microwave or sono, not converted, you say extracted. We extracted the lipids, and then we do trans-esterification and got biodiesel. And later on, we said a one-step direct trans-esterification. Namely, and we used either microwave or sonochemistry with a strontium oxide, as you see. Methanol was reactor, and we got, as you see down there, 37.1%. But if you take into the account what are indeed the amount of lipids, it leads to 99.9 conversion of the triglyceride to biodiesel. Here is a table or a figure showing that, you see, direct means direct sono, direct microwave in the middle shows directly. I have to stop for a moment. No, okay. Direct means that in one step, doing trans-esterification directly on the microalgae. X-trans mean extraction and then trans-esterification. And you have also reflux. And you see that the best is direct microwave, close to 100% conversion of the biodiesel. X-trans is also close to 100%, but remember that it takes a long process, a two-stage process, first extraction and then trans-esterification. Okay. Here, we went on and we worked on jatropha seeds and other seeds as well. We broke them down and have done trans-esterification directly on the content of, you see the white content of, this is a castor seeds, but it's the same. And indeed, here and with the biodiesel, it didn't take 10 seconds. It took 5 minutes, but still the conversion was very high, as you see here, 99.95% conversion of the triglyceride to biodiesel. And here is again trans-esterification, comparing sono, the microwave. Everything is in papers. You can read my papers and get all the information. Moreover, this was done about 12 years back. And so I don't remember all the names. I am very old, so I don't remember all the details. And it's better if you read the paper. Later, we have decided to do it in a flow system. This is a microwave oven. They can you pack the catalyst in its center, flow, of course, cooking or cooked oil and not fresh supermarket oil because that will cost a fortune. And we have done it, we have built the system and run it, and here you see the biodiesel coming out, and well, you should get the message. The message is that it can be done in a flow way. Again, details in the literature, but I should emphasize that here we took another care to remove the free fatty acids. That is essential. Now, all of you know very well that if you take glucose and you take yeast, you can ferment it and get ethanol, do wine, produce wine, and you have carbon dioxide as a gas coming out of the fermentation process. This is an old process. If you know the Bible, there was a guy, Noah, that came out of the flood and grew wines, fermented them, and drank the ethanol and got drunk. Okay, so you say 3,000 years, this process is known. What can be done in this process of the fermentation of glucose? First of all, Saccharomyces cerevisiae is baker's yeast. This is also, we got it, or we are still getting it from the supermarket. We go to the supermarket, we buy baker's yeast, and it's always available because people are cooking cakes and other things, they're using baker's yeast. So back to my question, what can be done? What is new, or what can be innovative in this reaction that is 3,000 years old? Well, we have tried to do the fermentation under ultrasonic waves to see if we can shorten the reaction. If the reaction under sonication, for example, can be carried out in a shortened way, and you save time on the time obtaining the ethanol. And the results are here. And if I asked, the answer is yes, we can indeed shorten the time. First of all, how did we follow the reaction? How did we follow the ethanol or the progress of the reaction? By two ways. Look at the bottom of the figure. You see, one is carbon-13 NMR. We followed the reaction. You see the base, 1 hour, 2 hours, 3 hours. Hours is the reaction time. And we followed it by carbon-13 NMR and weight loss. What does it mean, weight loss? After all, you know that glucose, the weight of glucose is 180, but the glucose in the fermentation loses 2 molecules of carbon dioxide. A molecule of carbon dioxide is 44, so 2 molecules is 88. In other words, the weight of the starting material is losing for every glucose molecule, half of its weight to gaseous carbon dioxide. And you see that we followed the reaction by this sonication and weight loss, and the sonication indeed is much faster. And here you see the glucose concentration was 20%, temperature was 30 degrees centigrade, sonication, we got in 5 hours 38% conversion of the glucose, but while stirring, only 14.5%. We measured the speed constant, and you see it's about more than twice, 2.2. The kinetics is faster. So another thing, okay, let's go on. Sonication by conversion. Full conversion was obtained in 19 hours. I don't believe that the wine growers, those who are preparing the wine, would be happy with these results, not because they don't like to shorten the reaction, but I think that they want the fermentation to go slow. That improves the quality of the wine. But as I said, I don't know enough about the wine industry. So here you have another demonstration. This is an important slide, because when I spoke to people that were familiar with fermentation, they said you cannot ferment more than 20%, a concentration than 20% weight of glucose. 40% glucose cannot be fermented because they are toxic to the yeast. But I said, look, I have to test it. And indeed we examined, and you can see that the reaction, the fermentation still goes on, even at 40%. And I think that sonication removes why is it poisoned by the ethanol? Because the ethanol sits on the surface of the yeast and poisons it this way. Sonication creates waves and creates a situation in which it doesn't let the ethanol stay a long time on the yeast, and it's less poison. Now, another thing in studying the mechanism of this fermentation is you see on the left-hand side that the yeast are highly aggregated. And we said, can we still enhance the speed of the reaction by the deaggregation of this yeast? So we have dispersed the yeast cell by sonication, and you can see on the right that the yeast cells are indeed dispersed well, but the kinetic did not go faster. In other words, it's not the aggregation that stops or slows down the reaction. It's the coverage of the surface. What the sonication does, as I said, is fast removal of the ethanol from the surface of the yeast. Various biomass, and here glucose, fuel. We have worked a lot in cellulose, converting into glucose and further to ethanol. I want you to show, this the biorefinery concept that you might know. Some of our effort was directed towards the preparation of levulinic acid. And in fact, about a month ago, we still published a paper on conversion of a microalgae to levulinic acid and further on. But levulinic acid is a material that you see It's a platform to the preparation of many other chemicals, and therefore we were going after it. Here are 4 different biomass that we worked on. Cotton.
Sorry to interrupt, but
and in another time, I'll continue the talk or go over to another topic, whatever you want. Okay, now I am open to questions. I guess my lecture was not clear to you.
we have one question.
Hi, Aharon.
Hi. Okay, go ahead.
Yeah, this is Barish.
Yes.
Thank you very much for this a kind and a nice presentation.
Okay. I'm glad to hear that you enjoyed
Yeah, I
it.
like to. Yeah, we enjoy. And also, I like to ask that you can say that microalgae could be a good source for the biodiesel. However, could you check the effect of the growing conditions on quality of biodiesel?
Quality of what?
Quality of biodiesel. I mean, such as every type of the microalgae could be used for production of the biodiesel.
You see, in general, not only when we have done biodiesel, but recently, as I told you, I have published a paper about a month ago from microalgae to levulinic acid. It's a fine chemical that is very important. Now, I am not growing the microalgae. As I said, I am a chemist, not a botanist. I have nothing to do. I am finding people that know how to grow. Now, in the case of the recent paper, we have done or we have searched the chlorella group. And in the chlorella group, there are a few chlorellas. And one of the chlorellas is chlorella ohadi. Chlorella ohadi has a high level of polysaccharides. And this is very attractive because if you want to go to levulinic acid and you start from a glucose and you convert it via a chemical reaction, a hydrothermal reaction, you need something of a lot of polysaccharides in it. Therefore, there will be a lot of glucose and a lot of levulinic acid. And this was the case. The people that are preparing the microalgae are searching for the chlorella that has the highest level of polysaccharides, and they found this special chlorella that is called chlorella ohadi. That's it. I don't know if I answered your question, but that is what I understood from your question. Any other question?
Actually, now you use this algs for production of biodiesel, isn't it? And I asked that, what is the climate condition or growing conditions effect on the quality of biodiesel?
Well, it was grown near the beach in the southern part of Israel, near the Gaza Strip, where there is, I would say, 8 months a year, there is sun. So they can grow during this period very efficiently, the microalgae. In the winter, I would not say that they are getting a lot of the microalgae. So versus climate, 8 months are appropriate. 4 months are less appropriate.
Thank you very much.
Do you have any other questions?
I tell you why I'm very, very busy. Next week, we have to submit an Israel-China proposal. And there are two topics. One is medical devices, and the other one is how the agriculture is addressing the climate change. I have decided to work because, as I said, all my life I worked on medical devices, antibacterial, antiviral, textile coating, and etc. I hope that you will invite me once to talk about the coating techniques that I have developed. But somehow, people that have submitted with me many years back a proposal from China, without notifying me, they are sending me now a proposal, and they are saying we are submitting it without asking me if I agree or not. I have to read it to see if they have changed something. Secondly, I am not sure that I am allowed to submit to proposal because this is related to burns on your body, how to heal your burns, and I'm not sure that I am allowed to submit. So I am in a mess. Therefore, 30 minutes lecture was enough for me, and in general, I am very busy. You heard that they are considering now elongating the date from 24 to 26 hours because I cannot manage to do all my work in 24 hours. So they are they are considering now to elongate the day to 26 hours. You see my problem. Therefore, I was very happy to stop it after 30 minutes to give you an idea, and I will decide with you, of course, whether to continue, when to continue. But now, in the next few days, I'm extremely busy. Thank you very much.
Thank you very much. Have a good day.
Thank you. Bye-bye.
Thank you very much. Bye.